Thank you. I am Henry Carter. I am the project manager for AS Engineering, and I'm also the water resources engineer. Behind me or to our right is Carly Sheen, our transportation engineer, Francesca Messina, our environmental engineer, and Darius Lane, our structural engineer. We've been tasked with the County Road 38 reconstruction project in Goshen, Indiana. With this, we are reconstructing a portion of the roadway corridor and County Road 38's intersection with County Road 21. We're also constructing a new visitor center and adjacent parking lot and designing a wastewater treatment facility and stormwater management system to go along with this project. As of now, our team has chosen our alternatives, calculated the construction cost estimate for our chosen alternatives, and we are ready to begin with phase 2 in the spring after approval from the owner. Here's Carly.
Thank you, Henry. Just to recap from the first presentation, my scope for this portion of the transportation engineering project is to improve the safety for all roadway users, including pedestrians, cyclists, and drivers, upgrade the level of service, and then stimulate economic development through the reconstruction of the corridor by stimulating jobs. Just to overcap kind of what my role is, I have to redesign a new intersection for County Road 28 and County Road 31. I have to realign County Road 38 with a 3-lane section. I have to add a multi-use path on the south side of the roadway, while also adding in a path underpass and reconnecting on the north side of the roadway, and designing a parking lot for the new visitor center. Some of the things that I've completed for phase 1 is I have evaluated my alternatives, I've chosen the best alternative, and then I have determined my construction cost. For my first alternative, it is a typical intersection with channelized right turn lanes. This alternative is deemed to have the worst level of service with level service F, which also means that it has the largest delay. But this one has the lowest construction cost, given that it is just a typical intersection with stop signs. My second alternative is a signalized intersection with channelized right turn lanes, and this was deemed to have the best level of service, which is level service B, which means it also will have the shortest delay, but the cost is in between this first and the third alternative. For my third alternative of the roundabout, this was deemed to have a level of service of C, which is in between the two alternatives, which means the delay is also in between the two alternatives, but the cost will be the highest out of the three. I then conducted an alternative ranking with my ranking matrix, given some different evaluation criteria, like safety and traffic flow and capacity were weighted as the highest. Given this alternative ranking, it was deemed that my second alternative of the signalized intersection with channelized right turn lanes had the lowest score, which meant that it had the best outcome with my matrix. I then chose the second alternative, given that had the best score for the alternative ranking matrix, and just given other criteria, it had the most cost-effective option, given that it was in between the two costs of the roundabout and the typical intersection. It had the best level of service, and I felt that it would not disrupt the community as much as a roundabout could, given that there's not many other roundabouts in the area. For my parking lot, I had two different alternatives, the first being just a regular rectangular parking lot with 122 stalls, and the second kind of being a little better configured for the new visitor center, and it had 131 stalls. I chose the second alternative for the parking lot, given that I thought it would flow better with the visitor center, and it also has more parking stalls, and I think it would just look better overall. For my alignment alternatives, I had two different options. The first one closely mirroring the existing roadway, having the multi-use path on the south side of the roadway and then heading north on the east side of the roadway. And this one I liked because it kind of closely mirrored the existing alignment and didn't disrupt as much as the second alternative that would most likely affect the business of the right here. And then, so I went with alternative one because I felt like it would be the least amount of land acquisition. It would not affect the homes and businesses as much. For my construction cost, I calculated the cost of the HMA, the concrete, and the cost of the signal. Those came out to be a little over $1.4 million. And then I had a miscellaneous cost being, because I haven't calculated how much I need for like my subgrade or other alternatives. So with a 35% contingency, my construction cost was deemed to be a little over $2.9 million. I will now pass it on to our structural engineer, Darius Lane.
Hi, yes, so my name is Darius Lane. I'm the structural engineer for AS Engineering. Here pictured is showing the site plan stating everything I've completed for phase one. So I selected my alternatives out of the three I presented previously in the progress presentation. And also I selected the alternative, and I've also completed the cost estimates for each of them. So here pictured is the preferred parking lot and my site plan that I've kind of decided to go with because they're in the shape that is chosen for this project. Here is the rubric that I've used in the matrix to kind of calculate each one that is scored based on the few of the criteria I've chosen. So from cost to constructability, aesthetic, and environmental impact. So when it came to cost, I kind of chose which one was the most cost efficient out of each three of the alternatives. The constructability, which one can kind of be constructed the easiest, kind of the fastest, and was most schedule friendly. When it came to environmental impact, it came to the components and material of each of the alternatives, and which one was most likely to either be recycled best or didn't have as much emission to when it was getting built or those type of things, and really just type of what happens to it at the end of the life when it was built or over time. And overall the aesthetics, so how it kind of looks to the consumer and the owner kind of approves, and how it looks to those that kind of just feel appealed and drawn to it, and overall to all the visitors. So as pictured here, you can kind of see that when it came to my third alternative here at the end, the L-shaped masonry walls and timber beams scored out to be the best. So the one having the lowest score, that is the one that shows it scored the best. So yes, it was the second highest when it came to the cost, but as far as everything else, it did show to grade out to be the best. So just a recap of all my alternatives here. The steel hexagon. This one totaled out to be a little over 40,000 square footage. I tried to keep everything around as close as 30,000 square footage as that was everything was part of the scope for this. And then for the additional outdoor area, I had 1,200 square foot for each of them. And so here is picture, you can see that it's covered, outdoor seating attached to the building on to each of the food court sections. And so when it came to the second level, that blacked out part right there, that is just showing that is kind of just the awning, so there's no type of extra load that will be there, so it won't be any type of exterior balcony. So it is strictly just going to be a roof, and that way they don't have to worry about any type of extra loads or liabilities to include as far as people walking on and those type of things. Moving on to my L shape for both the concrete and the masonry timber. This is the layout for it. Again, you can kind of see that my covered floor outing for outdoor is attached to the food court, as I felt like when it comes to most visitor centers, you kind of have the food court and then you also have the outdoor seating kind of right there in the picnic area. So I felt it would be best to kind of keep that theme for each of the alternatives. And so then again, my additional outdoor area was still 1,200 square feet total, and this one is a little bit bigger, but I think it helps out a lot to utilize a little more space and have a lot more inclusion and more people in there and just a higher capacity overall. For my preferred alternative, I did choose the L shape, but I chose specifically the masonry walls and timber beams, as this one totaled out to be a little over $8 million, and it graded out best in the matrix. Again, as previously stated, it was the best potential for aesthetic and creative freedom for the architect and so forth, and I felt this would be best approved by the owner. It was the lowest environmental impact due to the components used, and most schedule friendly and constructible. So as far as when it comes to masonry and timber, those are the ones that kind of be built the quickest and efficiently when it comes to construction, and usually doesn't cost as much. And again, pictured here, I just wanted to include my column spacings for this alternative. So they are very similar, kind of where the columns are, but there's a little bit less within that ground floor just due to the lobby area and so forth. And I just kind of wanted to incorporate a little bit more space and freedom when it comes to that. And then I had a little bit more columns in this first floor and the second level just to incorporate for the roof. I'll now be passing it on to Francesco for the environmental.
Thank you, Darius. Just to review my scope for phase one of the study, I to design a wastewater treatment system that accommodates future use and expansion. With this treatment system, it must include primary, secondary, and tertiary treatment, as well as disinfection. This system must include a disposal structure and have a minimum of 1 million gallons per day. The system must use the latest treatment technologies and comply with all local, state, and federal regulations. For the completion of phase one, I have evaluated all 3 of my alternatives. Within this evaluation, I made a criteria matrix to determine which one is the best. I have selected my alternative, and with the selected alternative, I have created a construction cost. The figure below shows 2 blue boxes that indicate the locations of the 3 alternatives. On the right, or the east, there would be alternatives 1 and 2, which would be the full-scale system. And on the west, there would be the alternative 3, which is the on-site mount system. Just want to briefly go over my 3 alternatives. For this first alternative, it is my full-scale activated sludge wastewater treatment system. It starts with the bar building to separate any of the larger solids, moving on to the aerated grit to get out any of the small grit or sand within the water. Then it moves on to the primary clarifier to get most of the total suspended solids out of the water. Then to the aeration tank to act as the biological treatment to remove any of the organics in the water. And the main part of the system is the secondary clarifier, which takes the remaining of the total suspended solids and compresses it to the bottom to create the activated sludge. This activated sludge is then pumped back to the aeration tank using RAS pumping to increase the efficiency of the plant. The tertiary part of this system is a disc filter to remove any of the outlying and total suspended solids from the water. And the disinfection of the system is a UV to disable any of the viruses and bacteria within the water. Then it flows to an outfall to discharge back into the river. For the second alternative is very similar, although the secondary clarifier and the tertiary treatment of the disc filter is placed within a membrane reactor. This membrane reactor uses 6 in-series membrane filters to filter out any remaining total suspended solids, as well as a small aeration part at the end of the filters to act as a small activated sludge part, where they would filter the activated sludge back to the start of the membrane reactor. My third alternative, this would be the on-site mount system that would be located west of the visitor center. This system takes the water directly from the visitor center, pumps it into the septic tank where the total suspended solids can settle. And right before the septic tank, there's a small filter in the pipe that would block out any of the larger solids. The septic tank then leads the water into the dosing tank that would dose it with chlorine to eliminate any of the viruses and bacteria. Finally, for the disposal of this, they would lead the water into the mount system that would let the water settle in the soil. For an alternative selection, I have 5 key criteria of odor, cost, footprint, aesthetics, and efficiency. Just going through all 3 of the alternatives. For the activated sludge, it's pretty moderate in each of the criteria. The membrane filter is best in the efficiency and the footprint, and the mount system is the best in the cost, odor, and aesthetics. Moving on to the larger matrix, I have ranked them. The weight corresponding is 1 is relatively insignificant, and 2 should be considered, and 3 is pretty critical to the process. So on the left side, you can see the evaluation criteria as well as its corresponding weight. Like the other matrices before, the lowest number is the best. So as you can see, the membrane has the lowest number, making it the best alternative. Just to highlight some of the more best parts of this, I wanted to look at the efficiency. So on the right side, you can see a table from the best design practices of wastewater treatment from Metcalf Netty in 2014. You can see the activated sludge system has 5 to 25 total suspended solids, while the membrane reactor has less than 1 to 5. With this, I also have the smallest footprint, made it best in its category. Going to the cost, I have gathered all of my concrete, whether it's the bar rack channels or the concrete for the actual basins, all from RS means. For this concrete, I used 4,000 PSI, which is just the standard for wastewater treatment. For all of the equipment, such as the clarifier equipment, I have used similar projects or direct manufacturers for their pricing. Specifically for UV filtration units, I've used the University of New Hampshire's capital cost equation for the units, and I needed 2 of those units to allow for redundancy. This totaled just over $6 million for this part of the project. With that, I'll pass on to Carter.
Thank you, Francesco. For For the water resources portion of this project, I've been tasked with designing a stormwater management system that can handle runoff from pervious and impervious areas within the project limits, and depositing this runoff into the Elkhart River watershed. I've also been tasked with reducing the nitrogen loads of this runoff by 50%. So far, I have evaluated alternatives. I've chosen the best alternative, and I have calculated a construction cost of this chosen alternative. Just to recap from last time, my first alternative involves infiltration basin and detention basin near the building area. Water will flow into the infiltration basin and infiltrate to the ground, removing this water from the system. And the detention basin, which sits around this infiltration basin, will collect any excess water from the building area and the west roadway area, which will then release it at a controlled rate back into the east side roadway system to then flow down into treatment and then into the Elkhart River. All water volumes from, or all water quality volumes from the roadway area will flow from west to east through treatment into the Elkhart River. Alternative 2 also has a detention basin near the building area. All water will flow into this detention basin to then be released into the treatment, which will then slowly release the water back into the main system right here along the roadway, and then all of the water will flow into treatment and then into the Elkhart River. Pros of this alternative are water quantities from the building area will be treated twice, right here and right here. Alternative 3 is similar in the roadway portion, but the building area will have an independent basin system with an infiltration basin and a detention basin. All of the water from the building area will flow into the infiltration basin to then infiltrate, but any overflow will run into the detention basin where it will remain before it flows back into the infiltration basin, and then all the water will flow to the ground. Pros of this are all water from the building area will be treated as it infiltrates the ground and becomes groundwater. Alternative 4 has an underground storage system right here in red, which is made up of manufactured media blocks with really high void ratios, 97% void ratio. And so what this will be is you'll construct it, you'll dig, you'll put these blocks in the ground, and then you'll cover it up. And then they are rated, or structurally rated by NDOT, and they are approved to go underneath roadways. So this can minimize footprint in that there's, we could put these media blocks under the roadway reconstruction, and water will then flow into there, and it will be treated in that this underground storage system will be constructed so that there's oxic and anoxic conditions, which allows for denitrification and nitrification of the water and release the nitrogen contaminant via nitrogen gas. Over here is a rain garden that is mostly to be a showcase along with the visitor center to showcase native vegetation and plants, but it is also going to be a functioning rain garden to treat some of the runoff from the building area. And on the east side of the river here, for all 4 alternatives, is a storm sewer system that is just collecting the water and depositing in the river without further nitrogen treatment here. This is because compared to the rest of the side, there's relatively low water volumes coming from this east side, and there's not a lot of footprint here to do treatment. For the ranking of my alternatives, I have evaluated them based on 6 criteria: cost, construction complexity, water management effectiveness, treatment effectiveness, compatibility with other design, and sustainability. Water management effectiveness and treatment effectiveness are weighted at number 3 because these are what is necessary for the alternative to achieve the project objectives. Sustainability is ranked at a 2 because over time it will improve the efficiency of the effectiveness of the system for management and treatment, but it does not it will not cause it to not be able to achieve the project objectives. Cost, construction complexity, and compatibility with the design are ranked 1 because while these are nice, they are not necessary in order for the system to function properly. Alternative 4 has been scored the best with a combined weighted score of 19. And this is alternative 4 again, and it is the option with the underground storage area. Other than the matrix, which was a quantitative analysis, qualitatively, alternative 4 works because it achieves the project objectives, it is simple, and it is sustainable. The construction cost for this alternative is seen here at just over $2,300,000. The bioswales, culverts, and rain garden costs came from similar projects in an estimation using that. The underground storage media was provided directly from the manufacturer specifically for this project, and the reinforced concrete pipe for the storm sewer system on the east side of the roadway, or east side of the river, comes from RF means. Overall, our team is ready to begin phase 2 for this design project at an estimated cost of just under $20 million. All we have left to do is finalize our individual design, then combine them and optimize them as a complete system now that we have all of our chosen alternatives. Thank you for your time. We are now open for questions.
Currently, on the level of service issues, is there a minimum level of service that's required?
I believe NDOT says a level of service C is the minimum.
Okay, so, and your alternative is kind of B?
It's a B, yeah.
Was there one that came out level of service C?
Oh yeah, the roundabout alternative was a level of service C.
Okay, so, but it costs significantly more, is that, and that becomes the reason why you didn't choose it? I mean, it meets the requirements of level of service C.
It does, yeah. I did opt for the roundabout just because it would have been a lot more of a cost, and there aren't any other roundabouts really in the area, so it would have been a bit odd for like the city of Goshen to get a roundabout, and also looking at the grading, it would be really difficult to put a roundabout at this intersection, and it would probably affect some of the homes and whatnot around the intersection, which I wanted to avoid as much as I could.
Okay.
So I had a question for Carly since you have a microphone. So about the roundabout, I would have guessed that the delay there would be less than the delay of the signalized intersection. It doesn't seem like there's a ton of traffic, and even roundabouts and more populated areas, I seem you can just kind of screw right through most of the time. So why does the roundabout have a bigger delay than the intersection? Can you convince me that really is true?
I was also a bit shocked. I ran this through Bistros, and that's where I got my level of service values from. I believe it might be because of the fact that there's only one lane going into the circulatory lane, but there are 2 circulatory lanes. I was a bit shocked as well that the level of service wasn't better, but I think once I added in the growth rate formula and like the future traffic predictions were entered, the level of service was a bit worse, so I think maybe that's where it came in. That's why this one was a level of service F, because it just wasn't going to stand the test of time. So yeah, I hope that answers your question, but I was a bit shocked by it as well, just because everyone always says how great roundabouts are, which they are great, but it just wasn't the right fit, I felt, for this intersection.
Yeah, thanks.
Thanks. So I have a couple questions. I guess the first with environmental on that side. So you have a mound system as one of the alternatives, and then kind of physical wastewater treatment systems for the other. Are they all treating the building by itself, or are they drawing in other, like wastewater sources?
Just the building.
Just the building
Yeah.
for that? Okay. And then the disposal is to the river? Is that, I mean?
Yeah, for the two that are off-site, it's to the river, and for the mound system, it'd be into the mound.
Okay. All right, thank you. And then, yeah, on the water side, on this side. So for your underground system, you drew in the costs.
Do you want me to go to the,
So like your
cost
final
slide,
cost. Yeah, it's like your final cost side.
right here?
Yeah, so, yeah, I like the idea of the underground kind of system, it's cool. You sold that pretty well. But do you know what the cost includes here? Is it the material, excavation?
So for this, I use a company, their project is R-Tank, and they have a spreadsheet that I don't have up here because it's multiple pages long. It's produced by a manufacturer. Basically, you just put in your water quantity, and then your footprint, how wide, how deep, and they come up with this cost, and they itemize it based on the material and the estimated labor costs and construction costs from, I'd assume, other similar projects that they've done. So I don't know how they do it necessarily, but their spreadsheet does estimate labor costs and construction costs as well as the material costs in that number.
Mhm. And is this kind of a shallow system that they put in, or?
It's approximately 6 feet deep, not counting I don't know off the top of my head, but for underneath the roadway, we need a certain amount of backfill above it, so I think it's 2 feet. So it's 2 feet below the roadway, if it's going underneath the roadway, and then 6 feet below that. So it is relatively deep, it might be obstructive, but we'll see.
Do you know, when that's right near the river, is there 8 feet of depth to the water table?
So as of right here, so there's a pond up here, and this goes into the wetlands. There is, depending where you choose, anywhere from 7 feet to 11 feet of drop if you look at the contour lines in QGIS. So assuming we keep it west of this ridge right here, then yes, it does work.
Okay. And just one comment before I forget, I wrote it on the paper, but you really should have some kind of treatment on the east, even if it's just some simple settling or something to get the large results.
Okay, noted. Sam,
Can you go to your ranking matrix? Like, yeah.
this one?
So, sorry, I just was trying to follow along. So the lowest number is the one you chose?
Yeah.
Oh, okay. So you ranked them 1 to 5 and did the multiplier, and 1 is the best and 5 is that right?
Yeah, so these numbers, each one has a 1, 2, 3, 4. Those are in relation to the other alternatives, so 1 is the best. It doesn't
okay.
necessarily mean 1 is by far the best or by far the worst or anything else. It's just that is discretely the best option, and then multiply it by score and multiply it by the weight. So this one, these are scored 1, 2, 3, 4. This one would have been 1, 2, 3, 4, but 1 times 3, 2 times 3, 3 times 3.
So I think I talked to you about this before, but is safety a criteria?
Safety is a criteria, but the reason it's not considered here is because all of my alternative options are not necessarily more or less safe. They're all going to be constructed to ensure safety, so there's not going to be a difference in the level of safety for my different alternatives.
All right, thank you.
Thank you.